Chalo bachcho, let's get started. Today we are going to learn a very important concept from our second unit, potential energy in an external field. Now I know the name sounds a bit heavy, but don't you worry. Trust me, we are going to make it super simple, and by the end of this, you will have it locked down for your exams. Pakka.
Okay, so before we jump into all the new formulas and definitions, let's just take a step back. We're going to start with an idea you already know really well from your Class 11 physics. It's the perfect way to build up this new concept. You'll see.
So just have a think about this. It's something you do every single day. You pick up a book from the floor and you place it on your study table. Simple, right? But to do that, you're using your energy. You're doing some work. So my question is, where does that energy actually go? Does it just vanish?
Exactly. It doesn't disappear at all. That effort, that work you did, it gets stored inside the book as you remember this gravitational potential energy. And here is the really cool part. Electric charges do the exact same thing. Bilkul same to same. They store energy just because of where they are placed in an electric field. This is the big idea for today.
Okay, look at this. This is a perfect way to think about it. Imagine gravity creates a kind of big invisible hill. When you have to push a ball up this hill, you're fighting against gravity, right? All that effort gets stored up as potential energy. Now, an electric field, it's just like an electric hill, but for a charge. So when you push a positive charge up this electric hill, meaning against the field, the same thing happens. The work you do gets stored as electrostatic potential energy. Simple, Hannah.
All right, so now that we have this electric hill idea in our heads, let's actually apply it. We'll start with the most basic, simple case you can imagine. Just one single charge, and we're placing it in an electric field that's already there. Okay, so it's time for the proper, formal NCRT definition. The potential energy of a single charge Q at a particular point is the total amount of work you must do to carry that charge all the way from infinity. I mean, from someplace super far away to that specific spot. And you're doing all this work against an external field that was just sitting there, waiting. It's like a landscape of potential that existed before our charge even showed up. And you know what the best part is? The formula is so simple, you'll love it. The potential energy, which we call U, is just Q multiplied by V. That's it, the value of the charge times the electric potential at that spot. So the main thing to remember is this. If someone gives you the potential, V, you just multiply it by the charge, Q, and boom, you've got the potential energy. All right, we're making good progress. So that was for one charge. Now let's make things a little more interesting. What happens if we decide to bring in a second charge? How do we calculate the total energy then? So let's think this through together. If we want the total potential energy of a system with two charges, Q1 and Q2, that means we have to find the total work done to assemble the whole thing. It's not just one piece of work anymore, is it? What are all the different jobs we have to do?
Let's do this logically, step by step. First, we bring in charge Q1 from infinity to its spot, R1. The work done? We just learned it. Q1 times the potential V at that point. TK? Done. Now, let's bring in the second charge Q2. First, we have to do work against that same external field, so that's Q2 times the potential V at its spot. But, wait a minute, there's a catch. Q1 is already sitting there, right? And Q1 has its own electric field. So when we bring Q2 closer, it's going to feel a push or a pull from Q1 as well. This means we have to do some extra work against the field of Q1.
And this third bit of work is super important. This is the work you do just because Q1 and Q2 are near each other. We have a special name for it, their mutual potential energy, or their interaction energy. And get this energy would be there even if that big external field didn't exist at all. It's just the energy of the two of them being together as a pair. So much may I?
So to get the total potential energy of the whole system, you just add everything up. It's the sum of all three parts. You have the energy of Q1 in the external field, plus the energy of Q2 in the external field, and you have to add their own personal interaction energy. That last part, the one with the 1/4 pi epsilon naught that you know from Coulomb's law, that's the energy from the two charges interacting with each other. And that's it. This is the complete formula from your textbook.
Let's just do a tiny example to see how easy this is. Imagine the external potential at a point is 5 volts, and we place a charge of +2 coulombs right there. What's its potential energy? It's simple. U equals QV. So you just do 2 times 5, and that gives you 10 joules. See? It's just a simple multiplication.
Okay, everyone, focus up for a second. I need to tell you about a very common mistake that students make in exams. This is one of those silent killers. It looks easy, but it can cost you marks if you're not careful. Let's make sure you never make this mistake.
Look very carefully at this screen. On the left, you see the formula for the potential energy of two charges when there is no external field. Notice it has only one single term, their mutual interaction energy. Now look at the right side. This is what we are studying today, potential energy with an external field. See the difference? It has three terms. The interaction term is still there, of course, but now we have also added the individual energy of each charge in the external field.
So please remember this. Whenever you have two or more charges, their mutual interaction energy, that Q1, Q2 upon R term, is always present. The external field just adds extra terms on top of that. In the exam, do not forget to include this interaction term. It's an easy mark to lose, but it's an even easier mark to get if you just remember this rule.
Chalo, excellent. That was the main tricky part, and you've got it. So let's just do a quick recap, a few key points to lock into your memory before the exam.
Okay, here is your revision checklist. First, potential energy is just the total work done to build the system. Second, for one charge, the formula is super simple. U equals QV. Third, and this is the important one, for two charges in an external field, you must remember to add all three terms. And finally, potential energy is a scalar quantity, so you just add the numbers. But don't forget to use the correct plus or minus signs for the charges.
And you might be asking, Sir, why is this so important? Well, because this idea of stored energy is fundamental in physics. This is exactly how capacitors work, the little components that store energy in your phone, your laptop, everything. It also helps us understand the potential energy of an electric dipole in a field, which is another big topic coming up next.
So, I'll leave you with one final question to think about. We've spent all this time talking about the work we do to hold these charges in place and store all this energy. But what do you think would happen if we just let them go? Where does all this stored potential energy go? Give that some thought, and we'll explore that in our next